All right, good afternoon, everyone. All right, well, let's go ahead and start with the roll. All right, Jimmy,
Here.
Joanna,
Here.
Ashley.
She has soccer again today.
All right, thank you. Yeah, I think she emailed me. Marissa.
She's coming.
All right. Caroline.
Here.
Courtney.
She's also coming.
Okay. All right, let's see. Jada.
Here.
Autumn.
I think she's on her way.
Okay. Matthew.
Here.
Weston.
Here.
Chan.
Here.
Kelly.
Here.
Seth.
Here.
Trey.
Here.
Kayla.
Here.
Tobias.
Here.
Nathan.
Here.
Rebecca.
Here.
All right. Okay, so let's see. Did Autumn come in? How about Courtney?
She came. Her and Marissa are here now.
Okay. And let's see. Okay.
Hey, Mr. Strong.
Hey.
I liked your megaphone yesterday.
You did, huh? Well, I do my best to try to pump up that lame volleyball crowd, but they usually do better at basketball and football, but I don't know, volleyball, it seems like it's harder to cheer at. Have you noticed that? It's harder. I guess maybe it's because of the way the action goes or whatever. But yeah, I was trying.
I feel like you just have to wait for like the really good kill and then it's good.
Right, exactly. Well, and I was trying to do that. I was trying to do that too, but we didn't have enough of them apparently. So, but you guys did great. I really enjoyed that game. You have a very talented team.
Thank you. Did you see us like waving at you like at the
Yes, I
second
did
game?
at the end. That was very nice. I appreciated that. But I wouldn't be surprised if you guys go far in the playoffs again this year. I was impressed with your team. I thought you guys showed a lot of skill and a lot of poise. It was a very nice match to watch. If any of you haven't seen, Mogion's volleyball team, you should go out and watch it. I mean, I thought it was wildly entertaining. So, anyway.
Yeah, hopefully we take state this year. If we don't, we're not gonna be very happy campers.
Well, sometimes I don't know. It's hard. Only one team gets to win, but I'll certainly be rooting for you when you get to the finals for sure. Anyway, that would be great. I would love that. It's funny how I guess this is how. I mean, I like teams that work hard and try hard, and win or lose, you're out there and you're just doing whatever you can. But boy, that when teams are do cheap shots or they're poor sports or whatever, I don't like that at all. To me, that really ruins it. But Anyway, just one little other volleyball tidbit that I'd like to throw at you before we get started is I actually did see the volleyball in the Olympics when they came to Atlanta. I got to see Olympic level volleyball, and it was just amazing. It was the Sweden versus China, and so Sweden had all these tall, beautiful blondes, and China had these just amazingly quick athletes that were just. I mean, I don't think the ball ever hit the ground on the China side ever. And it was an unbelievable match because it was like Sweden had all the offense and China had the best defense I've ever seen. And anyway, you want to guess who won?
China.
China won. Yeah, they were. And it's funny because the Swedish girls could block everything, but they'd miss some shot, they'd miss stuff or whatever. But China, they were amazing, their defense. I've never seen anybody lay out completely for a dive and do the perfect bump like that. I mean, it was just like unbelievable. But anyway, I'm sure you've seen all that, but it was cool. So anyway, well, let's
Wait.
Go ahead.
I have a question.
Oh, go ahead.
Okay, so for homecoming week, we have kind of like a beauty pageant just for the guys, and I'm part of it.
Okay.
But I need a good pickup line. So does anyone have a good pickup line?
Do you want a calculus pickup line?
Sure, or just any pickup line.
I mean, if you want a calculus pickup line, you could say, I want to be your derivative so I can lie tangent to your curves. I don't know, maybe that's a little much. I don't know. But that's a pretty good calculus line. I don't know. But I don't know. Somebody else want to help him out?
Jimmy, do you have one?
I don't have any off the top of my head right now. I'm sorry, man. If one comes up, I'll let you know.
Okay. All right. Well, let's see. How about, let's see. What's the one that used to make me laugh? Let's see. You probably heard this one. Are you from Memphis? Because you're the only 10 I see. You heard that one? Anyway. All right. Well, all of mine have numbers or something in them. So.
Tell me.
I have one.
What was it?
All right.
So, do you like raisins? And then if they answer, you say, well, do you want a date?
That's pretty good. That's pretty good. All right, you're writing these down?
Yes, I am. Thank you.
All right. Well, if you guys think of a better one, then we'll have to have a dating advice on Fridays or something. But anyway, let's get on to math. We are being recorded here, so for posterity's sake. So, all right. Well, go ahead.
I just arrived just now.
Oh, who is this?
Autumn from
Autumn.
Hopi.
Okay. All right. Thanks, Autumn. All right. Okay. So we've got a little bit to go here in chapter 2, and then we're going to start in on chapter 3. Okay. So a little bit here on 2.6, two-sided infinite limits. Okay. So if the function approaches infinity from each side of a vertical asymptote, we say that the function approaches infinity. So again, this is the deal is that the limit technically doesn't exist, but we say that it approaches infinity. So again, on both sides of the vertical asymptote, if they're the same, then we say the limit is infinity. Okay? All right. So, for example, you can actually look at the graph here on both sides of the vertical asymptote, as x approaches 0 from the left and 0 from the right, the function is going to infinity. Okay, so from the left, infinity, from the right, infinity. And so in general, we would say the function is approaching infinity because the left and the right hand limits are the same. All right, so try that one. See if you can figure that one out. So you can either try plug in numbers or you could use the graph. All right, Joanna.
Negative infinity.
Negative infinity is correct. Okay. All right, any questions on that? Okay, great.
Hey, Mr. Sean.
Yeah?
So I tried to graph it, and mine just says error syntax. How do you fix that?
Let's see. Okay, so you graphed y equals -1 over x squared.
Yes,
Okay, did you use the subtraction key or the negative key?
the negative key.
Okay, so all right, I don't know what would be the syntax error on that. Okay, let's just take a look at it. So just kind of follow my keystrokes. So we'll go to the y equals, clear that. And so we have -1, so use the negative key, -1 divided by x squared. All right. Okay, so my guess is that if you look at your window, there's probably something wrong with your window where like your x min is less than your x max or your y min is less than your y max. So to just fix that easily, just do zoom standard, and that should fix you to the standard viewing window. So did that help?
Yeah, I graphed it again when you did it, and it worked now. So I
Okay.
don't know.
All right, good deal. Okay, so any questions on that? But I'm glad you're asking because we need to, we want to work out all these bugs in class so that you don't have a difficulty like on a test or something like that. All right, next. Various behaviors of rational functions. So a rational function functions can behave in various ways near the vertical asymptote. But we're going to want to find the vertical asymptotes because that's where things happen. That's where the function goes to a positive infinity or negative infinity, or on both sides, one side. Usually that's a place where we look. So here, like if we have this one, this limit here, all right, and this is one where if you try plugging in 2, you get 0 over 0. So then you try to factor and cancel. So if you remember at x equals 2, where that factor canceled, at x equals 2, what's going to be on the graph there?
A hole.
A hole. And then here, where the denominator would be equal to 0, at -2, that's where you're going to have a vertical asymptote. Okay? Now, but as far as just finding the limit, all we do is we factor cancel, then you try plugging in again, and so you get 0 over 4, which is 0. And so that's very possible. I mean, so there's nothing wrong with 0 as an answer. You just can't have 0 over 0. Okay? All right? I'm going to do a bunch of examples. So just kind of watch me really quick, and then I'm going to have you do a bunch of them. So just kind of watch and take notes if you need to, but if you don't, just kind of look. All right? So again, this one would be one where you plug in 2 and you get 0 over 0. Okay? So you try to factor and cancel. Now, when everything cancels in the numerator, you're left with a 1. Okay? And so then you have 1 over x plus 2. Now you plug in 2 again, and so you'll get 1/4. All right? So you could get 0, you could get another number, whatever. But you try to factor and cancel. All right? So with this one, you plug in, and you don't get 0 over 0. You get -1 over 0. Okay? So now, anytime you have a constant over 0, the answer is going to be infinity or negative infinity. Okay? And so we've just got to figure out which. So if you imagine plugging in numbers slightly bigger than 2, basically what you have to figure out is if the numerator and denominator are going to be positive or negative. So if you plug in numbers slightly bigger than 2, this would be negative, this would be positive. Negative divided by a positive is negative, so the answer is negative infinity. Okay? And you could always look at the graph if you get stuck. Say, as x approaches 2 from the left, the y value is, this is 2 from the right, excuse me. Then it's going to negative infinity. Okay? All right, so with this one, we plug in 2, we get 0 over 0. And so now, can we cancel this? Can we cancel this factor with one of those?
No.
Yes, we can. Because it's an algebra trick, okay? Thanks for playing, though. But the idea is that see if like 2 plus x and x plus 2 would be the same. You could just cancel. But when it's minus, it's like you factor out a negative. See, 2 minus x is the same thing as negative x plus 2. If you just change the order. And then if you factor out a negative 1, then you get x minus 2. So that's how you cancel, is you factor out a negative 1. And then you can cancel. And so then you're left with this. Okay? All right, now you plug in 2, and you get a constant over infinity. So then your answer is either going to be infinity or negative infinity. Well, negative over positive, that's going to be negative infinity. Okay? Am I going too fast? You guys get what we're doing here? Okay. All right. So I'd like you to try these problems here. So practice 12, A, B, C, and D. Go to an E and F. So all of them. right, so Courtney, what do you have for the first one?
0.
0 is correct. Okay. Any questions on that one? All right, Weston. Second one.
I'm not sure on this one. I couldn't get a.
Okay, were you able to factor and cancel?
Yeah, I got 1 over x plus 3.
Okay, and so then you just put in the 3 again, and so you get 1 over 3 plus 3, or 1/6.
Okay.
Okay. All right, any questions? All right, Matthew. Oh, whoops. Guess we're down here. So for C.
Negative infinity.
Negative infinity is correct. Good job. Any questions on that one? All right, Caroline. B.
Positive infinity.
Positive infinity is right. Let's delete that. Okay. All right. And all right, Autumn. E.
I couldn't do that problem because it didn't show up on my paper.
All right, well, so C is the limit as x approaches 3 from the right. D is the limit of the same function as x approaches 3 from the left. And E is the limit as x approaches 3 in general. So just based on these last two answers, what would the limit be in general?
Oh, it would not exist.
It does not exist, okay? Because these limits don't match. All right, and the last one. Autumn again. So I suppose this one didn't, F didn't show up either. Is that right, Autumn? Did this one show up?
Yeah, it blinked out my whole second page.
Okay. All right. Well, let me have you write it down if you don't have it, and then I'll give you a minute to do it. So the limit as x approaches 3 of 3 minus x over x minus 3 squared.
Professor,
Yes.
so for example C, what did you plug in 3, but for example D, why did you plug in 2.9?
Oh, because it's close.
Well, okay. These were actually done by different students, but here, if you try plugging in 3 here, let's see. Yeah, actually, it would probably be better to do 3.1. So you plug in a value slightly bigger than 3. But if you try plugging in just 3, and here you get -1 over 0, then that tells you that your answer is going to be infinity or negative infinity. But really, you should, like you say, plug in like 3.1 just to make sure that this is negative, this is positive. So let's show that. So if we do like 3.1 minus 4 over 3.1 squared minus 9. Really, the focus here is that this is negative, because this tells you your answer is either positive or negative infinity. So this is positive or negative over positive, so this would give you negative infinity as your final answer. Okay? Got more clear now?
Oh, yeah, thank you.
Okay, you bet. Thanks for the question. All right. So, Autumn, do we have that? F?
Would it be negative infinity?
Negative infinity is correct, because here, let's get rid of this. Okay, so once again, you get a constant over infinity, and so then your answer would be positive or negative infinity. Okay. All right. It looks like, though, we've got a little difference here. Makes me wonder if we did the other one wrong. But here, if we plug in a value slightly less than 3, then we're going to get positive 1 over infinity, which is infinity. If we plug in a number slightly bigger than 3, then we'd get negative over a positive, so that would be negative infinity. But if we plug in a value slightly less than 3, then we'll get positive over a positive, so we would get positive infinity.
The book on the other example that you did says it was negative infinity, and you get the same answer as you would for this problem. So
Well, was it talking about the limit in general? Let's see. Okay, with this one, okay, let's see, this example. Okay, wait. Oh, I already canceled that factor. Okay, so the numerator is always negative. And the denominator, okay, that's it. So I'm not looking at this. I need to be looking at this right here. So here the numerator is always negative. But, okay, so the denominator could be positive or negative. So if x is slightly less than 3, then it should be, okay, so I shouldn't have changed that sign here. Whoop, wait, what just happened? I lost it. Come back. Okay. Let's,
Hey, I think I got your pickup line.
okay, go ahead.
It's absolutely terrible. Are you sure you want to hear it?
I am positive.
If it's inappropriate for a school setting, I don't want to hear it.
I mean, there's no profanity.
You know what I'm saying? I mean, if
Yeah,
it's
no, I know
terrible
what you mean.
because it's not funny, that's one thing. But if it's like super sexual, I don't want to hear it.
Well, I was gonna say,
Dale says it.
one for you is like diarrhea. I just can't hold it in.
Oh, okay. So that's just gross. I mean, okay. You want to be a little classier than that. Okay. How about this one? I can't believe I know the first 50 digits of pi, but not the digits of your phone number. How's that? Okay, let's try. Okay, let's go back to this one. We really have to decide what's going on here. All right, so we factor out a -1 and we cancel one of the x minus 3's. So this is what we're looking at now. So as we look at the limit as x approaches 3 from the left, so say 2.9, then 2.9 minus 3 is negative, so we have a negative over a negative, so that's positive infinity. All right, then if we approach 3 from the right, then we get, let's say, 3.1. So that would be a negative over a positive. So that would be negative infinity. So therefore, the limit does not exist. So that's the answer for that one. Okay? Any questions on that? All right, I didn't realize we still have actually more to this section than I thought. Okay. All right. So rational functions. Oh, we talked about this. The rational functions at infinity. I don't know why there's a lot of repetition in this section. Compare powers of x. If the degree is greater in the numerator, then the limit is infinity or negative infinity, and that's where you get an oblique asymptote. Okay, so I guess it's just focusing on that. So, and remember from yesterday, how do we find the oblique asymptote?
Division.
Yeah, polynomial division. Okay. No. Okay. All right. So for this one, if we want to find the limit, okay, if we want to find the limit and the power is greater here, then the answer is infinity. Or negative infinity, but it's positive over positive, so this is going to be positive infinity. So you don't have to go through how the book shows this is dividing by the powers of the exponent. You don't have to do this. If the problem just says find the limit. Oh, wait, this is the limit as x approaches negative infinity. Sorry. So as x approaches negative infinity, basically you just have to say it's either going to be infinity or negative infinity. Okay? Because the power is bigger in the numerator. Okay? So when you have negative infinity, let's see. Let's just look at it from the beginning. If you have negative infinity to the fifth, see that's going to be negative infinity. It's like a negative to the fifth power. And so that's going to kind of swamp so the numerator is going to go to negative infinity. The denominator is going to go to positive infinity because it's negative infinity squared. So negative over positive. So the answer is going to be negative infinity. Okay. Now, if you ever get stuck on these, just graph it. Just look and see what, here the graph would be going to negative infinity. So you could see that. Or as x is going to negative infinity, the y would be going to negative infinity as well. All right? So see if you can reason that one out. All right, Jada.
Negative infinity.
Yep. Okay, so since the power is bigger in the numerator, then the answer is either going to be infinity or negative infinity. This is going to be positive over negative, so negative infinity. All right, any questions on that? Okay, now we can also do the delta epsilon, the precise definition of a limit with limits at infinity or with infinite limits. I'm not really going to ask you questions like this on the quizzes or the tests though. But instead of requiring f of x to lie arbitrarily close to L, so instead of our target being close to the limit, we require f of x to lie arbitrarily far from 0. So how far from 0? Well, we say as far as you want. Okay. So if you want it to be a million, a billion, however far from 0 you want. And then we find the appropriate epsilon. But that's kind of the big difference there. Okay. So again, what we do is, so instead of our target being at some limit point, we just say, okay, we're going to let it be a certain distance from the limit, from infinity, excuse me. Or that we have a certain distance from 0. Okay, so we'll just kind of work through this one together. It says prove that the limit as x approaches 0 of -1 over x squared is negative infinity. Okay, so you choose epsilon to be within a certain distance from 0. Okay, now if we're saying that the function is going to go down to negative infinity, to show that we're just picking an arbitrary value that's negative. Okay, so there's nothing magical about -12. We're just going to say we're going to let epsilon be less than -12. Okay, and then we're going to find a delta that will get us that will work for that. Okay, so now we'll just choose some arbitrary number 2. All right, so now when I plug that into the function, -1 over 2 squared is -1/4. Okay, So is negative 1/4, see, negative 1/4 would be right here. We want it to be with past negative 12. Or let's see, no. Oh, we want it to be past negative 12 because we're trying to show that the limit is going to negative infinity. So basically this first choice, it didn't work for us. But that's okay. I mean, we're just sort of guessing and checking here. So it didn't work. We wanted it to be past negative 12. So now we choose another value, okay? And probably pick one closer to 0. So we're going to pick 0.001. So now if I plug that into the function, I get negative 1 over 0.001 squared, and that's negative 1 over like a million. So negative 1 million. So when x is 0.001, my y value is at negative 1 million. Well, that one works because that one's past negative 12. Okay? So I just kind of wanted to show you kind of how that works, but like I say, I'm not going to really test you on anything like that. Okay? All right, any questions? Okay. All right. Vertical asymptotes, horizontal asymptotes. That's kind of what this section has been about, is finding the asymptotes. And then once you get the asymptotes, it helps you find the limits. Okay? So let's just look what each asymptote is telling me here. So here we have a vertical asymptote at y equals 0. So that means the limit of this function as x approaches 0 from the right, since it's going up, is positive infinity. And the limit of the function as x is approaching the vertical asymptote from the left would be negative infinity. It's going down. So on both sides of the vertical asymptotes, we want to check stuff. Then the horizontal asymptote is where you check the limit of the function as x approaches infinity. The y value is going closer to 0. And then as x is approaching negative infinity, and in this case, it's also approaching 0. Okay. All right, so to find the vertical asymptote, you set the denominator equal to 0 and solve. To find the horizontal asymptote, that's where you take the limit as x approaches infinity, or compare the powers. And then to find the oblique asymptote, that's where we do polynomial division. Okay, anybody need more time on that?
Can you scroll it up again?
Sure. All right, you got it? Okay. Okay, so for here, so to find the horizontal asymptote, it would be y equals what? Y equals 1 over 1. The vertical asymptote would be x equals, what would make the denominator go to 0?
-2.
-2. So x equals -2. Okay? All right, so we're running out of time here. So if you would just find those asymptotes, and we'll go over those tomorrow. Practice 15. Sorry we didn't get finished, but we'll pick it up there tomorrow. Okay? All right, and then if you have a good pickup line, I guess you can bring that tomorrow. Or is today your deadline on that?
Yes,
Yes.
it's tonight.